Why try to invent a different algorithm? I'm honestly curious. Yeah.
So I noticed that they were unweighted edges, and so I just used the neighbor's algorithm. It seemed easier to implement and faster than doing full-blown breadth-first search.
Okay, so explain what you mean by a neighbor's algorithm.
So if I see a vertex, I just explore all the children, and then I add those all to a list. Actually,
it's breadth-first search.
That is breadth-first search. Never mind. I'm crazy. Never mind.
Are the people who do these other algorithms here?
Well, man, I don't know. I mean, I'm not trying to. You can even speculate about what other people other than yourself would do breadth-first search. Yeah.
I have a question. So you said people try to do variation of breadth-first search.
Yeah.
Would a variation be like stopping it sooner or something like that?
Well, I'll tell you a variation I saw. It was a variation where the graph, rather than being represented with an adjacency list, was represented with a list of edges. Right? So that was the entire graph representation. Just imagine a list of pairs. Now, what's the problem with that? It makes it much less efficient. To enumerate the edges out of a vertex, you've got to look at every single edge. And you've got to do that for every vertex. So suddenly the main loop of breadth-first search becomes E times E, and which is at least V squared. And then, of course, the algorithm doesn't terminate in time. So that's an example of taking, we talk about standard representations, but you have to use them. Yeah.
I was say one thing I noticed, a lot of algorithms that use breadth-first search will wait until the algorithm is completed, and then use the product of the algorithm, meaning the previous and distance array. But you can actually get for this problem, you can actually get the information you need as the algorithm is running. You can pull out the names and put them pull off at a certain point, when they're useful, sort them, and then stuff them into
okay, and I saw a lot of that, and I'm wondering why. There seems to me there are two phases to this: search, sort.
Why is it skip the second half? It's faster.
Yeah.
I was just going to say, if you, since there are multiple rumors for a single graph, if you just do the algorithm on the graph first, which this is your point, you just do the algorithm on the graph first, and you don't have to redo the algorithm at a time, and maybe you could potentially stop, but you can use the product of, the single algorithm for the multiple rumors. So I was just going to do that on why you might not stop early.
Okay. Yeah.
I actually don't get that, because isn't the whole point you measure the distance from a vertex, and if the vertex changes with the width.
Yeah, if the start vertex changes, you can't reuse the breadth-first search. Start at a different point. Yes?
Seems like trying to save time, to try to pull up the information while the algorithm is running, while the breadth-first search is running. It seems like you're just trying to save through. If you don't do that, then all you have to do is just go through your results of breadth-first search once. That's just going to go through everything n times, or d times, right? So I guess it seems like that's not very important, because it doesn't change the complexity of the algorithm. It's just adding a v time iteration.
Right.
If that makes sense.
I mean, you got to do v breadth-first searches. I think the major complication I saw that people made was they do a breadth-first search. So what they're trying to do is they're doing a breadth-first search, and they change breadth-first search to try to notice when the distance from the vertex changes from, say, 4 to 5. It's going up by 1. At that point, they stop. It calls breadth-first search. They take some names they've accumulated somewhere. They sort them. They print them out. And then they resume breadth-first search. So it complicates breadth-first search. My question is, why not just run breadth-first search, be done, and then sort the array? Very few people did that. Okay. So how do you do the sort? Do you wait to the end? Yeah.
You can write it, at least in C#, you can either compare it or you compare it by distance and then by name.
Right. You write a custom comparator to your sort that pairs first by distance, we should compute it. And if that's a tie, it does it by name. That way you keep the sorting completely separate from the first search, because when you try to merge the two things into one, you suddenly got a custom algorithm. It's much better to stay with stock algorithms. So anyway, I just wanted to mention that because I was surprised at how different a lot of the algorithms I looked at were. They just weren't standard. I didn't see very many standard graph searches. Okay. Any last questions or comments about that? Okay. That brings us to this week's CAS problem, which I suggest you use a Dijkstra's algorithm. You're going to have to modify it, but it's not exactly a shortest path algorithm. So that one you've got to modify, but it's just a few slight customizations you need to make. Now we'll talk about this. This is a problem off the assignment last week. So there's the problem. Assume you're familiar with it. We're trying to find the shortest sequence of pourings that gets us to a stopping condition. And what was the way to do this? How do you model as a graph? What kind of graph? What kind of graph algorithm? Okay.
So each node or each vertex is the amount in each of the three containers. And
Okay, so each vertex is what I call a state. It's how much is in each of the three containers. So it's a sort of a situation you can be in. Okay, let me get the next thought from you.
Each edge is a transition between states.
Okay, so each edge is a legal pouring that gets you from one situation to another situation. Okay, what kind of edge? What are the edges like? Yeah, it's directed. They're directed edges. Sometimes you have an edge from the state and an edge back. Other times you don't. What kind of graph algorithm would solve the problem? Yeah.
Shortest path.
Shortest path, or in this case, it's mouse to graph for a search because the edges aren't weighted. All right, that's well and good. Now, let me just go. That's just a picture of what we just talked about. How would you implement this? Let me describe one way of implementing it and see what you think. Okay, so how many different vertices could there be? Yeah?
Many.
Many, okay. How would you calculate how many vertices there can be? Yeah?
Perhaps a decision tree.
Say what?
Perhaps a decision tree.
No, you don't need a decision tree.
Oh, they're at most select 10 from 2 from 10.
Well, so how big are the containers? 10, 7, 4. So there are 11 situations, 11 states that 10 pint container can be in. 8 and 5. So it's just 11 times 8 times 5. That'd be how many vertices there could be. Some of them may be impossible, but we don't know that. All right. So let's say we got that number of vertices. We create them all. And then we go and find, for each pair of vertices, we see if there's an edge between them, and we put it in. And then we find, now we got our graph, and we find the start vertex, which is going to be the 0, 7, 4 one, and we do our graph first search. So, what do you think? Yeah?
So doesn't just creating a graph cost quadratic time?
Okay, creating a graph would be very expensive. And every pair of edges, every pair of vertices I talked about, it's going to take quite a bit of time to build the graph, even just to search it. So that doesn't sound like a good approach, does it? So how do you look at this problem and say it's a graph problem? It's just theoretical, a theoretical graph problem, and you solve it in reality, you solve it in a different way. What's this got to do with graphs? Yeah?
You can keep track of what states you have, so if you see the same state, don't add it to the graph. That way it'll just
Or you're trying to explain how to build the graph more efficiently? Okay. Still, it's a fairly large graph to build, yes?
I'm trying to find the shortest path. Why don't you just build out until you find the path that works?
Okay, so he said the key word there, build out. You don't have to. In a lot of graph algorithms, you do not build the graph and then search it. Right? The World Wide Web is a graph. If you want to search the World Wide Web, do you build a separate representation of the web and then search that? No, you'd spend forever building the graph. You just start somewhere and see where you get. So when this is a bona fide graph problem. It is a breadth-first search problem. But it's not sort of a classical, here's the graph, do breadth-first search on it. So we don't build the graph completely and search it. Instead, we start with a single vertex. We create a vertex, and we figure out what other vertices and edges there are from it. So rather than building the edges in advance, when in breadth-first search, when you get to the point where you've got to follow all the edges out, you figure out what all the edges are out at that point and follow them out. And add vertices to the queue as necessary. So when you're done, when you find the shortest path, you will have only generated a small portion of the graph. You wouldn't have built the whole thing from scratch. So let me just make that concrete by showing you a Java program that does that. All right, here's my state class. So I have 3 instance variables, which is just the number of, well, I was saying pints, now I'm saying liters, but anyway, the amount in the 3 containers. I have a way here to get this. I can construct the initial state right there. I can construct an arbitrary state right here. And this is the key method here. You give it a state, you return the list of states that you can get to from this state by one pouring. So it's just looking at a bunch of situations. It's trying to figure out which, is it legal to pour from the 10 to the 7, or from the 7 to the 10, or whatever. So each of these is figuring it out. And there's a set of states, there's a list of states that it's being added to. So we get back some number of states that are reachable from the current state by a pouring. So where would this method fit into a breadth-first search algorithm? Yeah? Right, when you're in the breadth-first search algorithm, when you're enumerating the edges in order to find neighbors, you would use this. Okay? So that's the bulk of the coding. That's the that just figures out what your neighbors are. I got a method to detect if I've reached a final state, and then I've got, I'm using a hash table, so I define equality in a hash method. Okay? And then here is the actual method down here, bsolve. Okay? So it takes 2 parameters, the start state and the previous array. Because we need to figure out, we need the previous array so we can construct the path at the end. So we find out what sequence of pouring to work. And it's just straightforward breadth-first search. We sort of, the previous array has already been initialized, but been created rather. But we add start to the previous array and give it itself as the parent. Create an empty queue, add start as the last, and we have the standard while loop for breadth-first search. And while the queue isn't empty, we take a queue out, we find all the neighboring states, and if we haven't been to that state, we add it to the queue, add it to previous, and return if we've reached a final state. So that's pretty much straightforward breadth-first search, except we are returning from the middle and generating neighbors a different way. So we generate the graph on the fly. This is very typical of graph algorithms that you see in the wild. Yeah?
So what if you create a state that has already What if you create a duplicate state with next states?
Well, right, if we get a state we visited before, that's possible in regular breadth first search as well. You can have an edge to a vertex you visited. It will see that it'll be in the previous array, and so we won't do anything. We'll ignore it. Okay. So then, when I'm done, this loop right here prints out the path from the loop. It just takes the previous array and works backwards from the final state to the first state. It prints out. So it prints out as it goes. So when I run it, it finds a path for me. Yeah.
Why don't you check if the volume 10 bucket has a volume of 2 in it? Why are you only checking the 7 and 4?
I think the problem said you had to have two in either the 7 and 4. Yeah.
So you see how this will definitely improve the average case, but will this not improve the upper bound on the worst case?
Well, I have to think harder about the problem to figure out what is the worst case for this? Is it possible to have to visit every state? I seriously doubt it is necessary or even possible to visit every state.
Yeah, I'm not speaking specifically just for this problem, but just in general, like the idea of building out while you're searching.
Yeah.
Does that guarantee to improve the upper bound on the worst case?
Well, I think I can't say it's guaranteed in every situation, but I mean, I would say almost every time it is better not to build the whole graph before searching it. I mean, think about you write a program to play a game of chess. So you can view you could model all possible chess positions as a graph with an edge between two positions if you get the one to the other with a legal move. But clearly, you don't start a graph program a chess program by building that graph. Although you are searching that graph when you're playing chess. If you're playing it in your head, you are sort of generating the positions in some fashion as you play, visualizing them. Yes?
Actually, it's a little bit unrelated, but for Rubik's Cube, from any state, you can solve it in 20 loops.
Mm-hmm.
So, I guess this is like that.
So Rubik's Cube is you can view it as a shortest path problem too. But people that can do that can solve any position in 20 moves are definitely they're not constructing the entire search space and then not doing a breadth first search. They're not doing it. They're good at recognizing patterns. They're not clearly not modeling the entire search space at once. Yeah.
So would this be a good example of generators you talk about in 3500, where we don't try to generate all the edges all at once, you only yield it?
Yeah. They're called them iterators in 3500. Okay. Now we'll go back to modular arithmetic. All right, we did this last time, so I'm just going to remind you where we were. So we're talking about modular arithmetic, and this notation here, this triple equals, is congruence or equivalence. And we say that two numbers are congruent, mod n, if they differ by a multiple of n, their difference is divisible by n. If you take x mod n, you get what? The same thing as if you take y mod n. Okay? So what you'll find is sometimes we'll use mod as an operator, like right there. We might say, what's 7 mod 2? The answer is 1. Other times we'll have the mod off to the right in parentheses, and we're just saying we're doing all this work mod 7. So we know 5 is equivalent, congruent to 12 mod 7, because they, for various reasons. 5 mod 7 is 5, 12 mod 7 is 5. That's one reason. But mainly, I look at it different ways to figure it out. If they differ by a multiple of the modulus, they're congruent. So anyway, we're using that notion a lot, congruence modulo n. Okay? And then we talked about the substitution rule. And essentially, the substitution rule just says that you can replace equals with equals, or I should say congruence. You can replace something with something that's congruent to it in an operation. So 14 times 25 mod 4, we can substitute for 15 anything that's equivalent to it mod 4. 14 times 25 mod 4. So what's something simpler that's equivalent to 4, to 14 mod 4?
2.
Okay, 2.
Yeah.
And 25 mod 4 is 1. So we're just saying that this modular arithmetic is equivalent to that. And that's just 2. So you can replace equals with equals. It's just the notion of equals here is different than usual arithmetic. We saw that one, 2 to the 345 mod 31. I can group it like that, and then I can replace that with something that's anything that's congruent to it, mod 31. In particular, that's 1 is congruent to it. So the whole answer is 1. So we'll make use of that, and we'll make use of the fact that these operators are, commutative, associative, and distributive, like regular arithmetic. That's where we left off last time. So let me pause here and see if there are any questions I could clear up before we look further. Yeah.
So in that example, you can only take the mod of the base and do it with the exponent?
Yeah, you can't. So the substitution rules up there apply to multiplication, or rather addition, multiplication, and exponentiation. You can only substitute into the base, not into the exponent. That is true. I'll let you puzzle about that. Yeah?
Is that because the exponentiation is like a lemma that kind of comes from the multiplication? Like,
Well,
it's like a side effect?
Yeah, it follows some multiplication.
Okay.
Yeah. Okay. So now we're going to look at algorithms for doing modular arithmetic. And the game we're playing here is, imagine we have arbitrarily long integers. So n-bit integers, little n. I'll use little n for the lengths of things. Big N is used for modulus. And we'll assume we've got some package that lets us do just regular arithmetic. Multiplication, addition, whatever, on integers. We need to come up with modular arithmetic. So, what will be the algorithm for computing x plus y mod n? It's not a difficult algorithm. Okay?
X mod n plus y mod n?
Well, we're going to assume that x and y are already in the right range. So taking x mod n isn't going to be useful. X mod n is already less than n. Okay, so you're given two numbers, two non-negative numbers less than n. Yeah.
Add x plus y and then mod the sum.
Okay, he said do x plus y and then mod the sum. So yeah.
X plus y and subtract n.
Okay, so there's two possibilities. Do we add x plus y and then compute, basically do a division and use the remainder? Or do we add x and y and then subtract n? Yeah?
Well, so yes, adding x and y and modding the result by n, but you optimize it and you don't actually do division because you're guaranteed that you're off by most. The most that could be off by is n.
Right?
So you just do a check to see, do I need to subtract n?
Right. So yeah, that is the idea. We add x and y, and then if you have to, you subtract n. If the sum is greater than or equal to n, you have to do a single subtraction. So that's preferable to the division, because division is more complex. So for example, 3 plus 5 mod 6 is 8 minus 6, which is 2. What would be the complexity of this? An addition and a division. An addition and a subtraction.
fairly,
Yeah?
should be close to constant time because we bounded the size of the inputs to n.
Well,
Unless n is large, is it?
N, capital N, what we're assuming here is that capital N has little n bits. So log of capital N is little n.
Okay,
So in terms of little n, the number of bits in the modulus, what's the complexity of a modular addition?
So in that case, it'd be linear time with respect to the number of
Yeah.
bits.
It'd be O of n, because you have to, the addition takes linear time, and subtraction does as well. So all three numbers have log n bits, and that's linear. So it's O of log n. Now, I didn't put it on the slide. I'll often, instead of writing O of log n, I'll do O of little n, where the deal is little n is the number of bits in big N. Right? How do we compute, how do we do multiplication? What would be the multiplication algorithm? Again, assuming that you have regular, you can do integer arithmetic, non-modular arithmetic. What would be an algorithm here? Okay?
So x times y, and then you just keep subtracting n until you get.
Well, we could do x times y and then do a bunch of subtractions, but that could take a very long time. What would be better? Yeah?
Can we potentially distribute mod n to x?
Well, again, there's no point in x is already assumed to be less than n, so distributing the mod will help. Yeah?
So instead of subtracting, just divide.
Right. We do a multiplication and then a division to get the remainder. So you do x times y, you divide by n, and you report the remainder. That's the answer. So 3 times 5 mod 6 is 15 mod 6, and then divide by 6, the remainder is 3. What's the complexity of that? Multiplication and a division, in terms of log division. Yeah?
That'll be O of whatever multiplication algorithm we decide to use.
Well, there's a multiplication step and there's a division step. And whereas we know there's a faster multiplication algorithm, there is no known division algorithm that's faster than n squared. Yeah?
Log n squared?
Right, so it's the square of that. Anyway, long way of saying it's just, it's n squared where n's the number of bits. Yeah?
In practice, division is done basically with multiplication. It's the same time complexity as multiplication.
So to computing a remainder,
Would be the same complexity as multiplication.
okay? I have to think about that. So how do you do division with a multiplication?
It may be a bit of a tangent I wouldn't want to go off on.
Okay. Okay. We'll leave it at log squared instead. So again, don't be, you look at that, where the log come from? It's just, this log n is a number of bits. Yeah?
I'm confused because aren't addition, subtraction, multiplication, division just one operation?
Not when we have arbitrary length integers, which we do here.
Oh, they could be bigger integers.
Yeah. They're adding the comment that I was making before. Okay, so we got that down. Let's do modular exponentiation. So the idea is, same setup, you've got x and y and n, and you want to compute x to the y mod n. How do you do that? Who has a suggestion?
Like you said previously, where with the example of 2 to the 5th, is like 68 or something like that. First, just take mod x.
Okay, well, x mod n, again, there's no point in that because x is already less than n.
Oh, okay.
Yeah?
I have a sort of divide and conquer way of doing it. So you take the first two x's, and then the next two x's, and the next two x's, until you get to about y. And then you multiply those two, then mod it, then multiply those two, mod it, and then you build up a tree, and then you kind of narrow it down.
All right. That sounds promising. Let's think of a more straightforward way first.
So you just
What's the obvious way to do it? What's that?
Wait. X times x mod n and then times x mod n times x mod n.
Okay. So we just do a series of multiplications.
No, we do multiplication and mod n.
I'm going to make it even simpler. Okay? We'll get your idea in a second. So what we do is we just we do x times x times x times x times x, y minus 1 times in a loop, and then we take the result mod in. Okay? That's probably the simplest way to think about it. So to take 4 to the 5th mod 7, we do 4 times 4 times 4 times 4 times 4, which is 1024. Take that mod 7, we get 2. What could go wrong? What could go wrong?
So if y is like somehow bigger than like 31 or 32, we're going to run out of memory.
Yeah, you start with small numbers. 4, 5, and 7 are small. So x, y, and n are going to be, even if they're going to be constrained anyway. You end up with an answer. The modulus is going to be no bigger than big N. But your intermediate thing, that 1024, could really blow up. Yeah.
So when you multiply 4 5 times when the approach says to multiply by y minus 1 times?
Well, I'm not counting them. You start with 4, and then you count the dots in there. How many dots are there? There are 4 dots to do 5, to do something to the 5th. Okay, well, let's figure out the complexity of this. The first multiplication is n squared, let's say. We won't worry about caret super multiplication. And the result is twice as long as the first number, as we started with. So n squared operations result has 2 n bits. Now, what's going to happen with the next multiplication? What will be its complexity? Or how many operations will it do? You're going to be multiplying an n-bit number by a 2 n-bit number. Yeah?
2n squared.
2n squared, and the result will be 3n bits. And then the next multiplication will be 3n squared operations, and the result will be 4n bits. And the last multiplication will have y minus 1 n squared operations and yn bits. And we add all that up, and it takes, it's omega of y squared n squared. Right? And you may look at that and say, that's not so bad. That's just a couple of quadratic expressions. But what's the difference between y and n? Where did little n come from? Which is actually the size of the problem? The size of the n. Is it y or n? No. Y is a magnitude. Little n is the number of bits in x, y, and capital N. So the size of the problem here is n. Little n. So we need to replace y with something that's roughly equivalent to it in terms of little n. So what is y in terms of little n? Yeah?
Log y.
Log y is little n, roughly. So that means that y is what?
2 to the n.
2 to the n. So think about it this way. Suppose y is 100 bits. Okay? And so n will be 100. Y, how big can a 100-bit number be? Two to the 100. So it's one thing to do something for every bit in a 100-bit number. It's another thing to do something for, for the magnitude of the 100-bit number. So it's a quadratic algorithm here. N squared is just noise. I mean, this is a disaster. And that's the time it would take That's how big it would be. That's how big the answer would be. So 2 to the 100 is bigger than the number of subatomic particles in the universe. You're not going to write that down. And we haven't even talked about doing the division yet. Okay? So that's not good. But he had a suggestion for improving it. What was your suggestion?
So we do multiplication, and then we mod n, and then we do the times x again, and then we mod.
Okay. So we're basically using our substitution rule by simplifying the product each time. So let's go see how that works. We can take the result mod in every time. So let's say we do 4 to the 5th mod 7. What we'll do is 4 times 4 mod 7 and we'll get 2. Next step will be 2 times 4 mod 7, we get 1. Next step will be 1 times 4 mod 7, we get 4. Last step is 4 times 4 mod 7, we get 2. So it's the same, we're doing the same number of multiplications. But we're doing that mod, we're modding the answer each time. We get the same answer. How do we benefit? It takes the same number of steps as before. Yeah?
Intermediate number is a lot smaller.
Intermediate numbers are always small. They don't explode. Okay? So let's think about the complexity of that. Every step requires a multiplication and a division now. The last time it was complicated because the numbers kept getting big, longer and longer. We had to account for that. Well, the numbers are staying the same here. So it's still, we're doing still y minus 1 steps. And that's 2 to the n squared. Okay? Now, is that an improvement over last time? I think it was 2 to the 2n or something, or 4 to the n.
So is that the best case?
It's still exponential.
So that's the lower bound?
Yeah, that's the lower bound. Now, it doesn't take so many bits anymore. The numbers don't explode. So that's not so good either. At least we could write down, we could write down the answer. Right? Let's get another way. What would be a fast way to compute, just for that special case right there, 4 to the 8 mod 7. You can see a fast way to compute that. Yes, Andy?
So you take 4 and 4, and then you combine them, but that gives you 4, 4, and then you mod it. Then now you take those two, and then you do it again, and then...
Well, I think there's a simple way to describe what you're doing, which is repeated squaring.
Yeah.
So we could look at it like that. X squared, square it again, square it again. And that gives you x to the 8th. Okay? So, and we would do a mod each time. So we do the 4 squared, and we take the mod, we get 2. We square that. We take the mod, we get 4. We square that. We take the mod, we get 2. So we get the answer. Okay? So repeated squaring works fine if the exponent is a power of 2. So here's a divide and conquer approach. So we got x, y, and n. If y is 0, that's the base case, the answer is 1. Anything to the 0 power is 1. Otherwise, we're going to compute x to the y over 2 mod n. So modular exponentiation, x to the power y over 2 mod n is what it's going to return. Now, the idea is we do that, and then what we do is we square z mod n, and that's our answer. Because if you take x to the y over 2, and then square that, you've got x to the y. Why is that not strictly true? It would look like if you take, if you compute x to the y over 2 and then square that, you get x to the y, yeah?
It's integer division.
Right, these are integers. So what we're saying here is, after you compute x to the y over 2, if y was even, yeah, you just square the result mod n and you're done. If it wasn't even, you're going to have to square the result and multiply it by an extra x to make up for the, let's say y was 7. So we just computed x to the 3rd power. So if we square that, we get x to the 6th. We need to throw in an extra x, so we get x to the 7th. So that's why we do the extra multiplication in that case. So let's see how that works. There's our 4 to the 5th mod 7 again. So it's going to, what's it going to compute first?
force. Oh, this is a recursive one, so we have to go all the way down to the tree and then go back up here.
Right, but so to compute 4 to the 5th mod 7, what recursive calls are you going to make? Yeah?
2 layers.
Mod X for 2.
Right, it'll divide, so there's our first call. So it's going to compute, it's going to try to compute 4 to the 2nd power mod 7. It'll divide that 5 by 2 and get 2. What recursive call will that make?
Mod 4.
Well, let me expand this out and we can see what's going on.
Oh, there you go.
So you can see the way the recursion is going. We call mod x of 457. That makes a recursive call to 427. That makes a recursive call to 417. This makes a recursive call to 407. This is the base case. We return 1. At this level, the exponent was odd. So we got to square the 1, multiply by the 4, mod 7, and we get 4. At this level, the exponent was even, so we just take our answer 4, square it, mod 7, we get 2. And similar thing at the top. So it's just an improved algorithm. So the question is, how complex is that? Yeah.
We've got to apply the master's theorem again, right? So the A in this case is we only make one call and we divide it in half every time. So the B is 2, and then D in this case would be a square since we got to do the multiply twice and the mod. So it would be, let's see, it's
All right, so you've worked it out in your head there.
So it's A is equal to 1, B is equal to 2, and D is equal to 2. So
All right, let's stop. Yeah, we can use the master theorem here. We can also look at it and say, how deep can the recursion go? Okay, so we're dividing y in half every time. So we can go log y deep. So the log y levels of recursion. What's another word for log of y? Little n. Number of bits in these numbers. So we do n steps. At each step we're doing 1 or 2 multiplications and a division. We'll call that n squared. So it's n cubed algorithm. N squared operation, each level n's the number of bits in these numbers. Basically, little n is log big N and n level, so it's an n cubed algorithm. It is a very important algorithm because this is the algorithm that's used for RSA, for public key encryption. It's, the encryption step and the decryption step is modular exponentiation. Okay.
Do you have an iterative version of this?
Yeah, there is an iterative version. Let's take a break and we'll look at the iterative version. All right, let's get started again. Okay, so that was our recursive modular exponentiation algorithm. Here is the iterative one. Okay? So the way the iterative one works is it looks at the bits in the exponent from high to low. So it starts with the high order bit of the exponent, goes to the low order bit of the exponent. And depending on whether that bit is even or odd, it either does our, if the bit is odd, if the bit is 1, it does the x times z squared mod n operation. And if it's even, if it's 0, it does it just squares the z that it's building, mod n. So it does the same operations as over here, but it doesn't involve recursion. How many times does this loop run?
And little n times?
Yeah, 1 for each bit in the exponent, which is little n. Just like this has a recursion depth of little n. And it does the same types of operations, so the complexity is the same. So the complexity is little n cubed, where n is the number of bits in the numbers. Okay? So like I say, that's it may seem kind of an esoteric algorithm, but it's bread and butter. It's used anytime you do e-commerce, modular exponentiation. So it's important that it be efficient. In fact, the RSA, we'll see eventually that because this is an n-cubed algorithm, RSA is not used everywhere it could be. It's a part of e-commerce, but it's not all of the other encryption algorithms used because RSA isn't fast enough for some applications because of this n-cubed step. All right, so another algorithm we'll need is greatest common divisor. And hopefully we all know what GCD is. GCD of A and B is the largest integer D that divides both A and B. And so we want an algorithm that works. We're going to analyze the algorithm for really long integers. So what's the GCD of 14 and 6? Let's just make sure we understand. 2. Okay. So the largest integer divides them both. 50 and 17?
1.
Yeah. 12 and 20?
4.
Okay. So here is Euclid's algorithm. You take the GCD of A and B. If B is 0, you return A. Otherwise, you return the GCD of B and A mod B. So it is recursive. What else do you notice about it? What kind of can you characterize it? The type of recursion? Yeah.
Tail recursive.
It's tail recursive because the last thing it does after recursive call is it doesn't do anything after recursive call. It return the result. So it's trivial to turn that into a loop. So it's not like an inherently recursive thing. So to do the GCD of 14 and 6, you have to, it computes the GCD of 6 and 2. So what you'll always see is the second parameter becomes the first parameter, and the second parameter, the new second parameter is the mod of the first two. And that's the GCD of 2 and 0, which is 2. GCD of 50 and 17, you get 17 and 16, 16 and 1, 1 and 0, and you get 1. And with 12 and 20, it's 20 and 12, 12 and 8, 84. Okay, so you see this going on. Okay, and we observed that you can easily turn the algorithm into a loop. Okay, now a couple things we can do. We can analyze the algorithm, or we can try to understand why it works. And you've seen it often enough. Maybe it's a good idea to try to understand why it works. So let's start with Euclid's rule. So this is what Euclid discovered 2,500 years ago. X and y are positive integers. And we're going to assume x is greater than or equal to y. Then the GCD of x and y is the same as the GCD of x minus y and y. First of all, why would Euclid's rule be interesting for talking about the correctness of Euclid's algorithm up here? Yeah.
Is it because when we did the modulus, we were subtracting?
Yeah.
10 slides ago.
So when we do, up here we're doing A mod B. Down here we're doing X minus Y. So when Euclid came up with this algorithm, he did not use, what he did was subtraction. Basically repeated subtraction for doing division, as you suggested earlier. And so this just justifies, you can simplify one step by subtracting off Y. That's not going to change the end. Okay, so let's look at the proof of that. So we want to prove that these two things are the same. First step, suppose D divides both X and Y. It must also divide both X minus Y and Y. Okay? So why is that?
Oh.
Yeah.
Because you can turn X and Y into like A over D and B over D, and then
Well, we don't.
A minus B over D.
There's a more straightforward way of looking at it. Yeah.
I guess because D divides both X and Y, so minusing something from X that is divisible by D, and if X is already divisible by D, then it's
Okay.
X minus Y is still divisible.
So you're both saying the same sort of thing. Suppose D divides both X and Y. Well, clearly, if D divides X and Y, D will divide Y.
Right.
Right? D divides Y, D divides Y. So the only interesting question is if D divides X and Y, it'll also divide their difference. Okay, so two things, basically we're saying they're the same modulo D.
Oh. And we already did that.
Yeah, we already did that. So if X and Y are both multiples of D, their difference will be a multiple of D. Basically what's going on. How do you conclude that? Yep.
If we could just do proof by contradiction and say if something divided GCD of X minus Y and Y, then, if it divided the first but not the second, then it would contradict our statement.
Okay.
So the GCD divides the first one, so it must.
Right. So the idea is GCD of X and Y, among other things, evenly divides X and Y both, right? It's a divisor. So we can think of GCD of X and Y as playing the role of D up here. The GCD of X and Y divides both X and Y. So it must also divide both of those. So we know that the GCD of X and Y is a divisor of these two things. And so it can't be bigger than the GCD of those two things. It's a divisor. It may or may not be the greatest divisor.
Can you give us more proof of all of this? And,
More proof.
yeah, the whole proof.
Well, that is the whole proof. Let's do it again. Do you agree that the GCD of X and Y divides X?
Yeah.
Do you agree that it divides Y?
Yeah.
Okay. Since the GCD of X and Y has that property, do you agree that the GCD of X and Y divides X minus Y?
Yeah. And then it also has to divide Y.
And it has to divide Y. So it's a common divisor of X minus Y and Y. It may or may not be the greatest common divisor, but it's a common divisor. So it's less than or equal to the GCD of those two things. This thing divides both of those, so it has, by definition, it's less than or equal to their GCD. And you know, I won't belabor the proof. You can do the reasoning in the opposite order as well. Yep.
You could also just say, so since D divides X, then you can write X as, say, D times another integer called maybe M or something. And then do the same thing for Y, say Y is like N times D. And so then X minus Y is D times M minus D times N. And then basic algebra says you can factor D out, D times M minus N, which is also an integer, so then you're done.
Okay.
That's
So anyway, we've got the inequality going both ways, so we know the GCDs are equal. So that justifies the key step in Euclid's algorithm. Now, let's work on the complexity of the algorithm. And so to get the complexity, we got to get some idea of how many steps it's going to take, how many iterations it's going to take over there, or how many recursive calls it's going to take over here. So we've got to figure out at each step what's getting smaller and how much smaller is it getting at each step. So here's my first observation. If A is greater than or equal to B, then A mod B is less than A over 2. Why is that true?
Shouldn't be less than B minus 1. Oh, because you stack two of them together in the worst case, and then you get a...
So why is it that, so we're saying the modulus A mod B is less than half of A. Yeah?
So when you, I'm not sure if I can explain what's in my head. When you mod it, like you're getting the remainder. I can't explain it. It makes sense.
Okay. There's a difference between understanding something and being able to explain it. So what's the deal? Yeah.
So if A is greater than B, then A mod B can't be B, and
Let me break it down this way. Suppose B is tiny. What do you know about A mod B? It's also going to be tiny, right? It's going to be less than B. What if A and B are almost the same? What's A mod B going to be?
Tiny.
It's going to be their difference, which is going to be small. So here's the idea. Suppose B is, so this is the case where B is tiny. B is less than or equal to half of A. Well, then the modulus has got to be less than B, which is less than or equal to A over 2. So if B is tiny, the modulus is tiny. If B is large, then A mod B is just the difference of A and B. And since we're assuming B is greater than half of A, what's left over is going to be less than half of A. So how does that help us do the analysis? When we take A mod B, we get something that's less than half of A.
Oh, can you see what a master's algorithm again? A master's theorem.
Yeah?
So we can apply the master's theorem again now that we know that we're halving the size and the worst case for each recursive call.
Well, we're having one of the parameters. There's two parameters. We're only having one of them. Yeah?
If you're just looking for a number bound, you can assume the two parameters start out at the same size.
Okay,
And
well,
just say after 2 iterations, you'll end up with something that's about the same smaller size.
right. So the thing to notice is, let's see. Well, I'll just put my analysis right here. So at most every other repetition A will be half, which is what he said. Okay? Why is it every other repetition?
Because you got to flip it.
Right, you do the mod and then it gets moved over into the first place. So if A and B are n-bit integers, that's at most 2 n repetitions. Because every other time A gets at least smaller by 1 bit. And each repetition is n squared operations we're doing, which would tell you that the algorithm is n cubed. O of n cubed. It turns out this analysis is overly pessimistic, that things have more frequently than that in general, and the algorithm is actually n squared. This is what this is saying here. So the algorithm, we didn't prove it, the algorithm is an n squared algorithm. The worst case turns out to be Fibonacci numbers.
So where does the square come from? Is it mods that cost a lot?
Yeah, and the divisions. Okay, let's see how it works with the Fibonacci numbers. So let's say we're taking the GCD of Fibonacci of k, the k Fibonacci number, and the k minus 1 Fibonacci number. So, okay, so the GCD of those two numbers would be this. Well, what is the GCD of the k Fibonacci? I'm sorry, what's f sub k mod f sub k minus 1?
F sub k minus 2.
Okay, so what do we know about f? We know f sub k is the sum of f sub k minus 1 and f sub k minus 2. So when you they're close, so you do the subtraction, you just get the you get that f sub k minus. Well, I'll just work it out here. You get that. So this is equal to that, and it just keeps going like that. Every step you get a smaller Fibonacci number, you eventually get down to the bottom. That's just an observation that the worst case for GCD happens when you give it a pair of consecutive Fibonacci numbers. Okay, so we've looked at modular exponentiation and GCD, which are two key components of the RSA algorithm we're building. Now we're going to look at modular multiplicative inverse. And this is where I run into a lot of confusion from students when I talk about this. So we say that x is the multiplicative inverse of a modulo n if a times x is congruent to 1 mod n. So it's just like in regular arithmetic. Two things are multiplicative inverse if, when you multiply them, you get 1. So 2 and 1/2 are multiplicative inverses. Same thing here, except we're talking about congruence, not equality. Congruence modulo n. So we're just, if we want the inverse of a, we find something we can multiply it by that gives us 1 mod n. So, what is an inverse of 2 mod 3? What can you multiply 2 by to get 1 if you're working mod 3?
Because then you have to times 2 times 2, that's 4, 4 mod
Right.
3, that's 1.
The inverse is 2. 2 times 2 is 4. Mod 3, though, that's 1. So 2 is its own inverse, mod 3. Okay. What's the inverse of 4 mod 7? 2.
So times by 2 and then...
Okay, so let me tell you what I do when I'm doing this. I'm looking for something I multiply 4 by that will give me something 1 more than a multiple of 7. So I say, okay, 4 times 2 is 8. That's 1 more than 7. Okay, so 4 times 2 is 8. Mod 7 is 1. So 2 is the inverse of 4 if you're working mod 7. Okay? No one blurt the answer out. Let everybody think about it for a little bit. Let's think of an inverse for 5 if we're working mod 8. Now, how many possibilities do you have to consider? How many possible answers are there? Okay? The answer has to be between 0 and 7. Those are the only unique numbers, mod 8. Anything bigger is going to be equivalent to something smaller. Can 0 ever be the answer?
Wouldn't that be like banging out or something?
You know, you can't have You know, 0 times anything is going to be 0, so that's not the inverse of anything. What about 1? 1's the inverse of 1, but it's not the inverse of anything else. So really, you just got to consider the numbers 2 through 7 here. Okay? Which one works? 5. Yeah. 5 times 5 is 25, which is 1 more than a multiple of 8. 1 more than 24. So 25 mod 8 is 1. Okay? Now, before we do this one, I know from experience that I will ask this on the midterm, not on the midterm, on the final. And someone will put 1/9. Okay? When we're working with modular arithmetic, we're not looking for fractions. We're looking for the answer is an integer. Okay? It has the property that you multiply that integer times 9, you get 1, mod 11. Okay, so there's a search space a little bit bigger here. Inverse of 9 mod 11. So something, multiple of 9, something, yeah, it's going to be a multiple of 9 that's 1 more than a multiple of 11. Yeah? 5. Okay. So 5 times 9 is 45, which is 1 more than the 44. Yeah. What's the inverse of 4 mod 6?
Here. 1, 0.
Well, and 0. Yeah.
Is there not one in this case?
There is not one in this case. So that shows us that inverses don't always exist. Now, if you're working with real numbers, as long as you're not talking about 0, there's always a multiplicative inverse. Okay? And so inverses don't always exist, so there's not one there. And here's how you can tell if an inverse exists. There's an inverse A mod n, as long as the GCD of A and n is 1. So the problem here is the GCD of 4 and 6 is not 1. The GCD of 9 and 11 was 1, 5 and 8, 1, 4 and 7, 1, 2 and 3, 1. So those inverses existed.
So you
Yeah.
have to be relatively prime? Is that what it's saying? That you have to be
Yeah.
relatively
Another word that's relatively prime. Okay. 4 and 6 are not relatively prime. They have a factor of 2 in common. Okay. So the first step in understanding this is to understand what a modular multiplicative inverse is. And clearly it's easy to, hopefully it's easy to take these small numbers and figure out their inverses. But imagine if we're talking about hundreds of bits, thousands of bits, huge numbers, and you're trying to find their inverses. This is the key step in RSA, in public key encryption. And so we need an algorithm to compute modular multiplicative inverses. Now, let me warn you at the outset. There are two skills. There is understanding the algorithm for computing modular multiplicative inverses, and there's being able to compute modular multiplicative inverses for small numbers. And few things are sadder on the final than I give a question like, what's the inverse of 5 mod 8? And I see students that are filling pages of notes with trying to trace through the steps of the algorithm I'm about to show you that computes modular multiplicative inverses. It's complicated. It's not a complicated algorithm, but it's just got lots of details to manage. It's a terrible way to answer questions like this. Questions like this, you just answer with trial and error. Yeah.
How big of the numbers are you going to give us?
How big are the numbers? Like that.
So we can build our own times table, but
Yeah. It's just, do you know what this notation means is what it means. Okay, so we need an algorithm for modular multiplicative inverse. And the algorithm depends on this factor. Which says if D divides both A and B. So if D is a divisor of both A and B, so if that's true, and you can write D in that form, then D is a GCD of A and B. Now, you may not see why that's true or why this is relevant. This turns out to be key to computing inverses. But for now, let's just try to understand the fact. Let's see why it works. Okay, suppose A is 8, B is 5, and D is 1. Okay, okay, so D clearly divides with A and B. Is D the GCD of A and B? Yeah, D, it's the GCD. So it's got to be possible. It's got to be possible to write D as A times X plus B times Y. So how can you do that? What's an X and a Y so that A times X plus B times Y is equal to 1?
Well, we're at 8 and wait. Well,
You can use negative numbers.
2 and minus 3.
Okay. 2 and negative 3. Okay? Because 2 times 8 is 16. Negative 3 times 5 is 15. Add them together, you get 1. Okay? So there again, the GCD of those two numbers is 2. So it ought to be possible to find an X and a Y. 30X plus 16Y to equal 2. So what works?
1 and 2.
-1 and 2.
Yeah, negative 1 and 2 work.
Could you
Yep.
also have 1 and negative 2? Or, oh, positive.
1 and negative 2 would give you
Yeah, negative 2.
a negative answer. Okay? So there's a proof, but I'm going to skip it. So that's the key fact, and then we're going to use that fact to come up with an algorithm. So we'll stop here, and next time we'll take this fact, build our algorithm for multiplicative division. Stefan wants to say something.
No, can you just state what's going to be on the midterm and what's not?
The midterm will cover through this week's assignment and last week's lecture. And the stuff that, first 6 weeks of classes. It doesn't include this week's lectures.
Doesn't include anything like this stuff.